I welcome you all for week 7 problem solving session. I guess thank you Krishna Kumar for joining, and I hope more students will join soon. Probably I will get started for today's class. And by the way, if you are viewing in YouTube, so um, again, if you have any doubts, please come next week and do ask me questions. All right. So this week, what we are going to do is, I looked at your assignments. The assignments were not, there were not any uh, like they were all word problems, right? So they were all testing your fundamentals rather than problem solving skills. For example, there is no uh, you don't need to apply certain formulas because the formulas are not fully derived. In fact, we derived governing equations in the this week's lecture. So basically, we reviewed the fluid mechanics. Probably you must have derived this already in fluid mechanics or fluid dynamics course. Here we again uh, reviewed few fluid mechanics. We derived certain equations. Basically, did mass, momentum, and energy conservation. And we stopped at energy equation. Uh, we are yet to derive temperature based energy equation. So that will be in your week 8, I guess. And all the questions were based on, assumptions and hypothesis, whether it's valid or not. And I guess you should be able to answer those questions if you properly uh, listen to the lectures. So I'm going to quickly review class notes today, what we studied in this week 7, especially after we started convection. In fact, this is not just week 7, it's also week 6 partly. Uh, Basically, when we started convection, what we studied, what are the equations we derived, what are the assumptions we made. Uh, so I'm going to quickly review that. And today's questions are going to be very simple. I'm not going to solve anything numerical. I'm going to go through some few five. I have like 5 MCQs. We'll just quickly go through that, and that will be all today. Okay. um so probably maybe reviewing it probably might be helpful if you uh, eh, for your assignments. So that's why I thought I will spend some, let's say, half an hour or so to review what we studied in the week 6 and week 7 regarding convection, and then we'll quickly go through these 5 problems. And if you have any questions, please shoot me an email, or you can also come back next week. Okay. All right. um, yeah, so we studied conduction, and we formally studied about steady 1D steady state heat conduction, unsteady heat conduction, uh, you know and 2D steady state heat conduction also we studied. And the next thing is of this course is convection, right? And convection is nothing but uh, you have a fluid flowing over a body, and that is going to help you in heat transfer. Okay, so that mode of heat transfer is what we call convection. And we basically did minor or basically we did a heat balance, right? Heat transfer balance along the surface where the fluid is flowing and heat is coming to the surface via conduction by some other means. And we basically did energy balance at the surface, so whatever heat comes to the surface is taken away from here. So basically we have a heat conduction equal to convection, right? And our ultimate goal is to find H. So basically in the convection, what we usually do is we find H. How do you find H? Till now, if you remember, in all our assignment problems we usually give H, right? H is like 25 watts per meter square Kelvin. But how did we get that 25? What is the analysis went behind to get that 25 is what we will be studying now. Convection. So what is this heat transfer coefficient? So it just simplifies all the complex processes happening in the boundary layer. So boundary layer is something you will learn soon, probably in the next week. So there will be a velocity boundary layer and there will be a thermal boundary layer, and within the boundary layer there's going to be a lot of things happening, and that is going to help you in heat transfer. And at the end you will be, your main goal is to find heat transfer coefficient. So once you find heat transfer coefficient, you will apply Newton's law of cooling and you will be able to solve the problem. Till now we have been given H, but now it's time for us to find H. Okay, so that's the whole exercise, or whole main, one of the main reason to study convection. Okay, and we as usual we did non-dimensionalization, and then we rearranged it and we end up having a new non-dimensional number called Nusselt number, which is HL by KF. Okay, this could be KF, this could be KS also, but it depends upon what is the temperature gradient here. I hope you understand what I'm trying to say. So usually we are interested in the fluid portion, and we always wondered what is the heat carried away by the fluid. So that's why we are interested in the temperature gradient in the fluid. So when you have a temperature gradient in the fluid on the left hand side, then automatically this K is going to be fluid's thermal conductivity. Okay, so you might also have seen a similar uh, non-dimensional number called Biot number, but however we use solid over there, and also the definition over there is a little bit different. It's about resistance, right? Conduction resistance over convection resistance. Here it's a little bit different. Okay, so this is the Nusselt number, and we also came up with an intuition that it should depend on these many parameters, and we also found that this rho u l mu k cp can be simplified, and you can write it as Nusselt number is going to depend on Reynolds number and Prandtl number. Okay, and so this, if we find the Nusselt number for a given heat transfer problem, then you can use this relation to find heat transfer coefficient H. And once you know heat transfer, K is just the property of the fluid. So once you know the heat transfer coefficient of the given problem, you can find what is the heat transfer. Okay, that's the complication that we have in convection. And to begin with, we started with Reynolds transfer theorem, which is a most general theorem, and you can derive mass, momentum, energy conservation. In fact, let's say if you have combustion happening, then you may need to solve for species mass fraction equations. You can solve for concentration equations. All these things can be derived from Reynolds transfer theorem. It's a more general version of any transport property. Let's say if you want to find how a transport property is going to flow within a system, you can just simply apply Reynolds transport theorem for that transport property, and you will be able to find a governing equation which is going to govern the flow of that transport property. So here that property, and extensive property, we call it N, and intensive property, I think we call it small n, right? And then we derive this Reynolds transport theorem. This is what we call it as RT. And if we change the n to be mass of the system, right, and which will make small n to be 1, we will end up having mass conservation equation. So that is what we derived. And dm by dt system mass is going to be 0. The change of, so the reason is, by definition system means fixed mass. Okay, which means the mass of the system will not change. So by definition you have dm by dt of a system to be 0. So that will end up having uh, your conservation of equation in an integral form, or here it's a mass conservation equation. So this doesn't have any uh, you know any assumption. So that is something you should note that. So, and then if you make an assumption of non-deformable CV, if the control volume is not changing, and if the control volume is stationary, then you will end up having, after simplification, you will end up having the famous continuity equation. So this continuity equation is also most general. It is not for incompressible or compressible flows. Okay, it's a most general. It's for all flows. All right. So this is the continuity equation, and now uh, we also introduced a concept called rate of volumetric strain, and then we rewrote this continuity equation, and finally we saw that this term over here will be 0 for an incompressible flow, and this term is going to be our simplified continuity equation, or basically del dot B equal to 0, right? So um, all right, and then yeah, we also found out that this, so density need not to be uh, constant to get an incompressible flow, right? So uh, basically, if it's an incompressible flow, only this part is 0. If this part is 0, then that eventually means, based on continuity equation, this part is 0. So if you satisfy this part to be 0, that is fine. No need to have density to be constant for an incompressible flow. Okay. So that is what we see here. For example, phase change is also could be used as, could be modeled as an incompressible flow because of this because of this reasoning. Okay. All right. And the next thing we started was conservation of momentum, and then it went a very long lectures. I think 2-3 videos it went just to derive the conservation of momentum. And you might have lost the overall picture of it. So the conservation of momentum, again, we start with anything, we start with the Reynolds transfer theorem, and the extensive property is the momentum, and the intensive property would be just velocity. You just substitute in the Reynolds transfer theorem, you will end up having conservation of momentum. Only thing is you have force. Now, what is this force? How do we find this force? Is one of the important thing, because right hand side is almost it's almost finalized. We just need to apply divergence theorem, and you will end up having control volume integral on both sides. Only thing is we need to find the force acting on a fluid particle, and we saw that there's going to be two kinds of force: surface force and body force. In the surface force, uh, body force, it's fairly simple. We have gravity force or any body force that is going to act on it, and you can just multiply with the volume. That would be the total force, right? The problem is this surface force. So we need to find out this surface force. For that, we introduce the traction vector, and the traction vector is something like force per unit area at any given point. It also needs an orientation to point out, and then we derived, we actually mapped the traction vector to the shear stress, to our any stress tensor. Tau ij is a stress tensor, and we call it tensor because it needs both direction and the surface. Okay, so that's why we call it tensor, because a vector you need a magnitude and direction. For a tensor, in addition to direction, you also need to know the plane on which it is acting. So there is additional information you are carrying with that. So that's why it is one step more than a vector. We call it tensor. Okay, tau ij, and we derived what is the traction vector for any arbitrarily oriented surface, because we are performing this analysis for a fluid particle. That's why, and the fluid particle can be any arbitrary orientation. So we should have a more general way of expressing traction vector in terms of stress tensor, and that is what we did. And finally, we ended up having uh, traction vector as a function of stress tensor. But in addition, we also need to know the uh, vector. We need to know the orientation vector, basically eta j. So, and the basically this is how you map the orientation vector to the traction. For any orientation, what is the force acting will be mapped by the second order tensor. Here it's a stress tensor. Okay, this is and in addition, we also did angular momentum conservation. So angular momentum conservation for any fluid particle is going to be summation of moments is equal to moment of inertia times the angular acceleration, and uh, we know these are the stresses acting on this fluid particle. So if you simplify this, you will end up having it basically gives you that stress tensor is symmetrical. Tau ij is equal to tau ji. It's basically symmetrical. And since because of that, what you can do, instead of 9 components you have only 6 components, and these two are same basically. The Yeah, that's what symmetrical means. So we can write the traction vector to be tau ij and eta j, tau ji eta j. Okay, so basically I can flip this j and I in the traction vector. Okay, not in the eta. In the traction vector I can flip this j and I. Still the traction force will still remain same. So once you find the traction vector, we can just simply write the total force is nothing but traction vector times the surface area in which it is acting. That will be the total force. And the body force, as I said, it's going to be simply a body source term times the volume of the control volume. All right. So now, since we have a control surface integral, we have to convert it into control volume so that we can find a differential form of our equation. So we'll apply divergence theorem, and if you apply Gauss divergence theorem to it, you will end up having a dot product of heat T traction vector, or in this case, traction vector will be replaced by stress tensor, so there will be dot product of stress tensor. Okay, so for that simplification, we are writing it like this, and then finally we write divergence of stress tensor plus B1. Okay, and uh, and you also know on the left hand side or on the right hand side we had this what do you call the time derivative and the spatial derivative. Basically these two equations coming from these two terms coming from RTT, and if you simplify them you will end up having this dou u by dou t rho u divergence of rho uv will be equal to these are the total forces. Now if you can even, this is for one component, we wrote it for one, we can write it as all three components in in a more general form in Einstein's notation like this. So this is your total momentum conservation equation, or you call it Navier's equation. Okay, um, so this is we applied both. This basically came from linear momentum equation. So if you remember, the extensive property was m into v, and the intensive property is just v. So basically it came from linear momentum equation, but this stress tensor is being simplified, and we found out that stress tensor is symmetric. So if taking that into account, we end up having this equation. So it's actually both linear and angular momentum conservation equation. Okay, so this symmetrical part is, we call it no body couple present in the fluid particle. Okay, all right. So this gave us three more equations because it's a vector equation. You can see you have one index in all the terms, others are repeating index, so all the repeating index you can replace it with summation. Okay, and so you are left with one index, which means you can write three equations with it. So we have three momentum equation and one continuity equation, we derived it. And then if you remember, if you know what is the unknowns, we have density u1 u2 3 velocities, and in addition we also don't know what is this stress tensor. We have the 6 stress tensors. So basically, unless we know what is this stress tensor, unless we express the stress tensor in terms of these parameters, we won't be able to solve this set of equations. We won't be able to get how the fluid is going to uh, flow around the system, right? Those things we don't know. That's why this is for more general fluid, so we need to close it. We need to find a relation of tau ij, or we need to replace it with some equation, and that equation is called constitutive equation. Okay, so we need constitutive equation to close the system. So what does this tau ij depend on? So basically we can divide this tau ij into two components. One is hydrostatic and one is deviatory. Okay, hydrostatic means when the flow doesn't flow, there is no flow in the system, is just static, right? If it is just static, then also there will be some forces acting on it, right? There will be some stresses in the system. Basically this hydrostatic is nothing but your pressure. Okay, so the pressure will still be there in the static system, and that's why you have separate hydrostatic stress and the separate deviatoric stress. Okay, and deviatoric stress is because of flow, and we know that deviatoric stress should be related to the velocity gradients. Basically, because of velocity gradients, because there is a velocity and the velocity gradients are present, you have a deviatoric stress tensor here. So we express this velocity gradient dou u I by dou xj in terms of rate of deformation, in terms of like it's just a mathematical manipulation. We can write it like this, and one part over here we can write this as a rate of deformation tensor. And so from Newtonian, if it is a Newtonian fluid, so from based on Newton's law, we know that stress is going to be dependent on uh, strain rate basically. So here this is the strain rate, the rate of deformation tensor is the strain rate. So the stress is going to depend on the strain rate. So that is why we wrote it as deviatoric stress tensor is nothing but some constant times the rate of deformation tensor. So now this constant, it's not really a constant. This is a tensor, this is a tensor. Now if you want to map two tensors, you need to have a fourth order tensor, which is going to have 81 unknowns in it, 81 unknowns. So basically what happened was you initially had two unknowns, and sorry, additional six unknowns, tau ij's. Now because you apply, it's a Newtonian fluid, now the six become 81, right? So now we need to find the C, I, J, K, L, everything. So you will have 81 unknowns. This is going to be keep on increasing. Now what you will do, you will again find how do I find C, I, J, K, and then you apply some other hypothesis or some other assumptions, and then that is going to go from fourth order, it is going to go to eighth order and keeps on going like this. So at some point we need to make assumption, we need to simplify this fourth order tensor. That is what we did here. We told ourselves that it's an homogeneous and isotropic fluid. And if it's homogeneous and isotropic fluid, we can just simply reduce this fourth order tensor into a much simpler form with just three unknowns, and we can reduce it based on this angular momentum. If you angular momentum conservation, if you remember, because these stress tensors are symmetric, we can reduce this further into two unknowns, and those two unknowns are simply alpha and beta, where it is lambda and mu. Okay, so one is volumetric dilatation coefficient, the other is viscosity, and the viscosity has this rate of deformation tensor. So this is nothing but EKL, which is what we saw here. Maybe it's EIJ. Okay, so and we have a viscosity here, and in addition we have volumetric dilatation coefficient multiplied by dou uk by dou xk. Okay, so this will be your stress tensor. Now if you know lambda and mu, your systems are closed because you are anyway going to find u, right? So you have expressed this six unknowns tau ij's in terms of u's, which reduces your unknown to just four. So now you will have four equations and four unknowns. You will be able to solve your system of equations. How are we going to solve? That's a different matter, but at least the system is closed, so there is a hope for solving it. Okay, so now only thing the remaining is we should give lambda and mu. We know mu is a viscosity, it comes from properties, and we take, we measure the properties and we know mu. Only thing remaining is finally this lambda. What is the volumetric dilatation coefficient? uh, so that is one thing remaining. We'll come back. So this is about deviatoric stress part. Now let's get into hydrostatic stress. In hydrostatic stress we had as I said, it's going to be pressure, and so pressure is compressive in nature, so you have a negative sign, minus P times delta Ij, and if you combine everything together, you are going to have this as your stress tensor, and you can write it in separate form. And then we introduced a concept called, this is mechanical pressure. So basically this is a stress tensor on the fluid, and pressure is normal component of it. So tau 11, tau 22, and tau 33 are divided by 3 is the mechanical pressure, and that need not necessarily be equal to the thermodynamic pressure. Thermodynamic pressure, we all know, it's going to be coming from the equation of state. Okay, it is going to depend on density and temperature. If it's a gas, it's going to depend on these two quantities. In fact, for most of them, it depends on these two quantities. Um, for liquid, it may not depend on these. Okay. All right. So we have this mechanical pressure and we have thermodynamic pressure, and in addition, we also have this part. Now, if we assume the Stokes hypothesis, which says that mechanical pressure is same as hydrostatic pressure, sorry, thermodynamic pressure, then we can simplify this whole thing into lambda plus 2 mu equal to 0, where lambda is minus 2 by 3 mu. Okay, so now we found lambda also, so our problem is solved, equation is closed, you can actually solve it. But your mechanical pressure is a function of pressure. We also need to find pressure now. Okay, till now the pressure didn't pop. We introduced new quantity called pressure. Till now our momentum equation doesn't have pressure, it just has stress, right? It was we started with 6 unknowns, stress unknowns. Now it has introduced pressure. Okay, so in order to find pressure, we know we have to use equation of state. Pressure is a thermodynamic quantity, so we will use equation of state, and the equation of state basically tells pressure is a function of density and temperature. And density we are anyway finding from continuity equation, so we need to also find temperature. Now temperature, to find temperature, what we have to do is we have to go forward and solve, or we have to derive another equation called energy equation, right? So basically now the pressure is also one of the unknown from the momentum equation. So you put everything together and then you will end up having this big equation, which we call it Navier-Stokes equation. This is most general, we didn't make much assumption, so it's just these are the assumptions that we made. This is also actually true for compressible flows. Even though you see this row outside, please be careful, it's also true for compressible flows. Okay, so as I said, uh, we have now 5 unknowns but still 4 equations because we added a pressure here. And now pressure, we can have an equation of state which might look like closing the system, but equation of state also introduces another unknown temperature. So we have another unknown temperature, so ideally we have 6 unknowns and 5 equations, so we need one more equation, and that equation is nothing but your energy equation. So once you derive your energy equation, basically you must you would have derived mass, momentum, and energy equation with the equation of state. Your total equations will be closed and you will be able to solve your problem. Okay, and a convection problem requires you to solve all these 3 equations with the equation of state. Okay, it's more complicated than conduction. Conduction, you just solve an energy equation and problem is solved, but a convection problem requires you to solve all these 3 equations. Okay, in that, one is a vector equation, it has 3 components. So basically you have uh, if it's a 3D problem, you have 3 momentum equations, one continuity equation, one energy equation, coupled with equation of state is required to be solved for a convection problem. Okay, that's why we are actually deriving all these equations. Okay, all right, so we understood that we need energy equation because we need to solve for temperature, and also we are in a heat transfer class, so right, so we should have an energy equation here. And again, going back to the same thing, we start from the Reynolds transport theorem, and the properties here is going to be total energy E, and intensive property is going to be specific total energy, small e. Okay, that is what we did here. And we already, I think, kind of did this during conduction also. So this is dou E by dou T of system is nothing but from first law of thermodynamics. You have Q minus W, and we need to find what is the heat transfer to the system, and we also need to know what is work done by the system. The heat transfer to the system is going to be either uniform heat generation. If there is a heat generation happening within the system, you will have heat generation, or heat can enter through the surroundings, through these surroundings. So that is what we have here. So that's why we have a control surface integral, and you have a heat flux vector. We don't know what is heat flux. We will learn that soon. What is this heat flux? Okay, so this heat flux vector, uh, and then you apply Gauss divergence, you will end up having control volume integral, which is nothing but divergence of heat flux vector. And then you have work done due to work done uh, work done by the system or on the system. We also need to know, because first law of thermodynamics requires that, are basically your energy content within the system depends on work done, right? So, and there are two work done. One is surface work and the body force work. And the surface work is done by the surface forces, body work is done by body forces. So that is what we do here. And we know surface forces are nothing but your traction vector, and the work done is nothing but this force times the velocity. That is what we did here. So, and we know to represent this traction vector in terms of stress tensor. So we did this, and then we end up having this big energy conservation equation, and we simplified it. And also we had this is heat generation, this is heat flux, and this is work done due to stress. It doesn't it includes both pressure and shear stress. Okay, tau ij is both pressure and shear stress, and bi uj is the body work. Okay, now the body force is nothing but your gravity, and this body work is nothing but your potential energy. So ideally this E, we initially started with total energy. If you remember, capital E is total energy and small e is specific total energy. That actually comprises of only internal energy and kinetic energy. It does not comprises of potential energy. Okay, although potential energy is also considered as a form of energy, here it comes as a force and work done. Okay, so that's why we have this bi ui. If you consider e to be in here, then you should not have this bi ui. Okay, so there is no potential energy, because bi ui is already accounted, which is nothing but your gravity or potential energy. All right, and so, but we are not interested in total energy. We need to find temperature out of it. So please remember uh, uh, the point of doing this exercise. We couldn't find temperature, also become an unknown, and we need to find temperature. Energy is not the energy. We cannot directly relate the energy to temperature. So if we could deduce this energy equation in terms of temperature, it would be helpful. So that's what we did, or we are going to do in the in coming week. So basically, to find energy, we know that this E is total energy, which accounts for both internal energy and the kinetic energy, and we know temperature is a function of only internal energy, right? It is not going to depend on kinetic energy. So somehow we need to remove the effect of kinetic energy from this total energy equation. So to find the kinetic energy, we took the Navier-Stokes equation, or the momentum conservation equation, multiplied with U, which gave us the kinetic energy equation. This is a standard format. Wherever you go, that is how you do it. Once you derive the total energy equation, you subtract it with uh, the momentum equation multiplied by U, which will be your kinetic energy equation. So basically, total energy minus the kinetic energy equation will give you the internal energy equation, uh, which you can use it to uh, write the temperature based internal energy equation. Okay, so that is what we did here. We know in total energy is I plus ui square, and Navier-Stokes multiplied by ui gave you this mechanical energy equation. You subtracted this, you will end up having internal energy equation. Now this internal energy, we know ei is nothing but, maybe you can write cv dt. Di is in nothing but cv dt, right? Now you replace this with cv dt, and you will end up having equation for temperature. So basically that is what we will do in the week 8. Okay, and uh, and then once you find the temperature equation, then together we solve all the Navier, the continuity, momentum equation, Navier-Stokes equation, and the energy equation together, uh, and our system would be closed. Okay, and okay, and we also did another a small what do you call exercise for this part over here. So basically this tells that this is the total energy change, total internal energy change of the system. It is going to depend on the heat generation which is happening within the system. So that if you have heat generation, the total energy is going to increase. So basically, right, because this is positive term. So this total energy is going to increase because of heat generation, and there is a heat flux vector. Heat flux vector is going out. So whatever the flux heat going out of the system is going to reduce the internal energy. That's why we have negative of heat flux vector. So if the heat is coming in, the heat flux vector itself will be negative. So then this whole term will be positive and internal energy rises. Okay, so this is taken care within the within this term itself. So in general, this is the net heat flux out of the system. That's why you have a negative term, negative sign in front of it. This is to intuitively understand. Of course, we derived it and we ended up having negative term here. But to intuitively understand, this is how it comes. And then we have a additional term because of the stress tensor, and this is actually we call it viscous dissipation, and this viscous dissipation is always positive, and that is what we for that only we perform this exercise. So this viscous dissipation, actually this is not purely viscous dissipation. So this is nothing but viscous dissipation plus a pdv work. You will have a pdv work. Okay, so basically tau ij is this. So this stress term will have a pdv work, and then you have this big thing, and this big is nothing but your, so this is nothing but your viscous dissipation term, this plus I guess these two terms. So this is nothing but your viscous dissipation. Probably I will write it here. So basically tau ij dou ui by dou xj is equal to minus p del dot v plus, I can simply write this as sum phi, and this is nothing but your viscous dissipation. And as the name suggests, it's going to dissipate the heat. Okay, so basically this is going to heat up your uh, yeah, it's going to heat up your system, or basically uh, you are converting your mechanical energy into thermal energy. Okay, so because of rubbing motion of fluid particles on top of each other, you have this viscous dissipation. If you do not have viscosity, if it's an inviscid flow, then you do not have this viscous dissipation. Okay, that's why it's also called viscous dissipation. However, you will still have pdv work. Pdv work will be there. Okay, even if it is an inviscid flow. So please remember that. So that is what your entire energy equation here corresponds to. So we will perform further manipulations, and we reduce in terms of temperature equation. And finally, in general, what they do in CFD is there are a lot of convection problems that people solve, especially in CFD. In CFD, what they do, they solve this equation in addition to this Navier-Stokes equation and the where is the other equation? Continuity equation. So basically, they solve these three equations together, and that is how they tackle the convection problems. And basically, they will also try to get the heat transfer coefficient from these small scale simulations, and then they will use this H over different places. Okay, so this is how you actually calculate H. So yeah, if you go back, we need to calculate H, right? And this H is nothing but a function of non-dimensional temperature gradient along the wall, right? If you want to know the temperature gradient along the wall, you need to know temperature. And if you want to know the temperature, since fluid is flowing, you also need to know how velocity, how density varies, and what are the governing equations which is going to tell about density, velocity, and temperature is this mass, momentum, and energy. So you solve these three equations, you find the temperature profile, how it is varying within the fluid, and once you find it, you find the temperature gradient along the wall, and K is a heat transfer property. You'll be able to find the H. Okay, that is how you find the convection heat transfer coefficient. That is the whole exercise that we are trying to do. Okay. All right. I think we took a lot of time on reviewing this. Maybe I will quickly get into some of the questions that I have. Today is going to be not really numericals. We are going to, I have like 5 MCQs. We can discuss that and we can close it off. By the way, if you have any questions, please let me know. I see that 3 more people joined. Thanks for joining, Satish, Avinash, and Mangal Lodi. So if you have any questions, or if you find any if you are doubtful about any derivations that we gone through during the lectures, please let me know. I'll be able to revisit it for you. All right. So I hope there's no problem still now. And let's just quickly solve this 5 MCQs, and then yeah, we'll meet next week. Okay. So the first question here is about. So I think it's going to be very easy for you guys today. So first question is here is about the continuity equation is a statement or expression or condition of which of these scenarios. Okay, so we are asking about the continuity equation. So is it a statement of mass conservation of fluid flow? Is it is a statement of incompressibility of fluid flow? Is it a divergence free flow, or is it a statement of irrotational flow? This is what they are asking. So what would be the answer? We all know it's a famous continuity equation. It is kind of like a simple question I'm asking you. So this is going to be simply the mass conservation of the fluid flow. That's what we derived also here. So continuity equation is nothing but your mass conservation equation. So the incompressibility and divergence free, all these things are special, what do you call, special cases of a continuity equation. So how do you get incompressibility? We saw that if you want to have incompressibility, then you will have del dot v equal to 0. The same goes for divergence free flow, right? This is for incompressible flow, incompressible, and that is what divergence free flow means. Irrotational flow is totally different thing. Irrotational flow is only valid for when v del cross v is equal to 0, right? Then only it's called irrotational flow, but it gets into fluid dynamics. We are not interested in at this point. Okay. All right. So second one is about simple. They are given the velocity components of a flow field, which is u is ax square and v is a minus. So let me write it down. U is a x square and v is minus a y square and w is 0. Okay. Now where a is a non-zero constant, okay, it is some constant. Which of the following statement is true for a given flow? Okay. So it is a divergence free flow. So first thing is, if it wants, we have to find out whether it's a divergence free flow. How do we find out? So divergence free means we know that del dot v is equal to 0. So probably maybe I will do this. Okay, del dot v is 0, and we know this is going to be dou by dou x I plus dou by dou y j dou by dou z k. This is a dot product of this del operator, and you have ui vj wk vector. If you find out and if it comes out to be 0, then it's a divergence free flow, right? So this corresponds to dou u by dou x plus dou v by dou y plus dou w by dou z. And since w is 0, we can simply write this down. Dou u by dou x also we can know. So it's nothing but 2 into ax minus 2ay plus 0, right? It's going to be simply 2a into x minus y. And a is a non-zero constant, so basically this is not equal to 0. Or you can say that del dot v is not equal to 0. If it is not equal to 0, what does it mean? So it cannot be divergence free flow, it cannot be incompressible flow. For incompressible flow, we need to have del dot v to be equal to 0, right? So the continuity equation, is it applicable or not applicable? What do you guys think? It's kind of like a trick question. So continuity equation, if you write this down, continuity equation would look something like this: dou rho by dou t plus divergence of rho u equal to 0. So basically this question didn't talk about density at all, right? So we don't know what is really happening with the density. So this could possibly be an answer. But if you assume that density is not varying, density is constant, if density is constant, then probably none of these statements are true. Okay. Anyway, this is something you should think about it, continuity equation. So continuity equation is always this is the continuity equation, and if whether the given flow field is satisfying this continuity equation or not, you should be careful. If they say incompressible flow, certainly this does not satisfy, this is some rubbish velocities. Okay. If it is incompressible flow and if the velocity u and v are given, then that should satisfy continuity equation. There is no other excuse. Okay. All right. This is much simpler question. What is this question about? The assumptions made in the derivation of Navier-Stokes equation. So simple, right? So so the first you know so in fact all the options has this continuum thing. This is something I don't know whether you guys are aware of. Probably you must be aware in your fluid dynamics itself. Here I don't think so. We thought about it much. So we basically assume all these fields are in continuum. Okay, which means that um, if you closely zoom down to molecular level, you have only molecules moving around. Even whether it is liquid, gas, or solid, doesn't matter. Those molecules will be moving around. Especially in solid, it will be stationary or vibrating or slightly moving up and down. But in liquids and gases, it's going to be moving, but all these molecules uh, will be independent of each other, right? Now, however, if you zoom out a little bit and if you consider, let's say, a bunch of particles, they as a bunch will follow certain characteristics, and that's why you can say that it is continuum in that level. Okay. Or in most technical way to explain this is, you have a lot of particles. Okay. Now let's say you are defining a density, okay, for this field. Let's say at this point what is the density? Okay, what would be the density if the molecule comes there? There will be some density. If the molecule is not there, the density would be 0, right? Now, however, if I zoom out and if I consider this big field, and if I want to know what is the density in this big field, then statistically we can say that some molecules will come and go, doesn't matter. Statistically we can say that let's say like there will be like 10 power 5 particles or something, So you can actually define the density, or in other words, let's say you have, this is your this is your volume, let's say delta V. Inside this, now if you increase the, if you try to plot density with this delta V, or the region of consideration, if you try to plot, so it will be something like this, and then it suddenly becomes almost, not suddenly, slowly it becomes almost constant. So which means in this region we are in a molecular regime, or we are our area of study is very small, such that it is comparable to the molecules. Now if you go above this critical delta V, then we can define properties. Then only you can define property. There is no such thing called density for a molecule, right? Molecule is molecule. That's what is density, right? But only if you zoom into a certain volume, then you can define these properties: density, viscosity, uh, thermal conductivity. There's no such thing called viscosity at the molecular level. So molecule, one molecule will go, one molecule will go there. What is the viscosity between these? There's no such things. Only if you go to a continuum level, only if you say that as a whole they behave as a continuous fluid, then you can define these properties: viscosity, thermal conductivity, density, all these things. Okay. So, and whatever we are dealing with in the present study, it's actually uh, in the continuum hypothesis. Okay, we are in continuum regime. Okay, all right. So yeah, so in that way you can, remove one of them, one of the options. So basically we are we'll come back. So basically this Navier-Stokes is for continuum, that is for sure. And uh, is it incompressible? So it is Newtonian fluid, that is one of the assumptions we made. And to simplify the stress tensor, uh, we you have two coefficients, dilatation coefficient and the uh, viscosity. So to reduce that, we introduce the Stokes hypothesis, right? So these are the main thing. And also we said homogeneous, only if you say homogeneous, the viscosity will be constant. If not, viscosity will never come, right? Then it becomes like a stress tensor, and there will be a viscosity tensor also. Okay, homogeneous and isotropic. So these are the assumptions that we made. We didn't make any incompressible or compressible while deriving Navier-Stokes equation. Okay, so in that way, if you see this says incompressible, so it's not steady flow, unsteady, it never came, which is the most general equation. And we are doing it for Newtonian fluid, right? Because Newtonian fluid means uh, the deviatoric part uh, is dependent on the rate of deformation tensor, right? If you remember, this is something we did. Okay, this is for Newtonian fluid. If it is not a Newtonian fluid, then it does not uh, behave like that. Okay, and so which will lead you to only this will be your answer. Okay, all right. I hope this is clear. If you have any doubts, please stop me anytime. Okay, all right. There's another uh, interesting question here. The simplest form of differential equation of for momentum conservation for incompressible Newtonian fluid, homogeneous fluid, Stokesian fluid, isotropic, and no body couple, no body force with constant thermophysical properties is given by which of these, is what they are asking. Okay, so instead of, I would say, uh, I usually do not like this MCQs, or showing us different options and asking us to select. I prefer to, given the question, let me solve it, and you derive the equation, and if you get the equation same as whatever the one of the option, it's better to directly deal with it. Okay, so we already, if you remember, so it's an Newtonian fluid, homogeneous fluid, Stokesian fluid, isotropic fluid, no body couple. So I think we took all these assumptions and we derived the Navier-Stokes equation. So we also, this is Newtonian fluid and also Stokesian fluid. So it's a Navier-Stokes equation. So let's say if I write the Navier-Stokes equation here, how would it look? Dou u I by dou t plus uj dou by dou xj ui is equal to um, minus dou p by dou xi plus there is this tau deviatoric. Where is this final form? In terms of lambda and yeah, this is the one. Dou by dou xj mu times dou ui by dou ui by dou xj. Okay. Yeah, this is the viscosity part, and there will be a dilatation part, which will be lambda times. Oh, okay. Lambda becomes 2 mu by 3. So yeah, we perform the Stokesian hypothesis. Right? So dou by dou xi mu by 3 dou uk dou xk dou uk dou xk plus bi. So now they said no body force, so we make this body force to be 0, and they also said constant thermophysical properties. Maybe we'll apply that, and before that there's also incompressible flow. Okay, if it's an incompressible flow, what we know about incompressible flow, we know that uh, your continuity equation will be, so dou ui by dou xi is nothing but 0, or basically del dot v is 0. That's what. So in Einstein's notation or in index notation, you write it as dou ui by dou xi equal to 0. Or this is also means dou uk by dou xk. It doesn't matter because this is a repeating index. You can change it however you want. This is also equal to 0. So there won't be any dilatation part, or this lambda part will not be 0. Sorry, lambda part will be 0, right? So this part also will be 0 because of incompressible flow. Incompressible flow. This is no body force. Okay, so this is how finally your Navier-Stokes equation is going to look like. So it's going to have this and this. It's going to have simply these two. Okay, now if you want to write this in vector form, you can write this as vector v dot del v. Okay, and this is going to be gradient of p. Maybe I will write it down here. Rho times dou v by dou t plus v vector dot del. So please try to understand why I wrote like this. Why not del v dot v? The reason is you have j here, you have j here, right? So that is what. So when you have two j's, those are the repeating index, which means you have a dot product between uj and dou by dou xj. Okay, so that's why you write it as v times v dot del. First you perform this operation and then you multiply that with the velocity vector. Okay, equal to minus this, you can write it as gradient of p plus this mu, you can take it out. If you take this mu out, what happens? So this is another del into, so you again see, so here you see dou ui by dou xj, which means this is a gradient operator. Okay, there is no dot here, so I have the gradient of v. Okay, now what is happening between this and this? You have two j's. Okay, which means it's a dot product between first dou by dou xj and second dou by dou xj. Okay, so which means you should have a dot here. Okay, this is what it means. So now divergence of gradient of V is nothing but your Laplacian of V. So we all know that. So we can just replace this part as mu times del square V. Okay. All right. So this is your final equation, and this equation simply satisfies this, which means this is your right answer. Okay. So only thing is you should know to convert from you should know to quickly go back and forth from the index notation and the vector notation. That you should be a little bit familiar with. And actually we didn't make you know constant thermophysical properties. Okay, yeah, mu is constant, that's why we took it out. Yeah, it's not spatially varying, so mu is constant, so that also in fact we took that into account. This is how your Navier-Stokes equation looks for an incompressible Newtonian homogeneous Stokesian isotropic no body couple no body force with constant thermophysical properties looks like. Okay. This is the simplest form you could bring it up. Okay. I guess it is clear. If there are any questions, please let me know. All right. So I have one more question. That's also again going to be very easy for you guys. For a Newtonian fluid, which of the statements are false? Okay. Uh, the shear stress may be a linear function of velocity gradient. It is not maybe. Uh, it's like it is the linear. Uh, but anyway, shear stress is a linear function of velocity gradient, and the deviatoric stress tensor must be a linear function of deformation tensor. That is all. That's also we know the Ij deviatoric is nothing but EKL, if you remember, right? So that's how we make it CIJKL EKL. So this is also true. Viscosity must be constant with temperature. Not necessarily, right? Viscosity need not to be a constant of temperature, constant with temperature. And D is none of the above. So they are asking which of the statement are false. So this is actually, it's not necessary. Viscosity need not to be a function of temperature. We never made that assumption, right? We no need to actually make that assumption. Viscosity, it could be a function of temperature, and we deal with that most of the time in our simulations. But what the Newtonian fluid tells is Newtonian fluid allows the viscosity to be a function of temperature. The Newtonian fluid just tells your shear stress is going to be a function of velocity gradient. Your deviatoric stress tensor is basically linearly dependent on rate of deformation tensor. Okay, so that is what your Newtonian fluid says. Other than that, it does not say anything. Okay, so that's why I think the viscosity must be a constant with temperature is not. It's actually a false statement. Newtonian fluid doesn't care whether your viscosity is constant with temperature or not. Okay. All right. In the way, this is the right answer, although it's a false statement. Do you guys have any doubts? So, if you're still having doubts in regarding the derivation, please go through the lectures once. Um, or if you have doubts, you can ask me. I can also help you with that. But if you go through your lectures properly, I think assignment 7 is should be very easy for you guys. Okay. These are just straightforward questions just to understand whether you made the right choice while deriving these equations. Okay. So that is about this week. Next week we will probably do some numerical problems, and also we will finish our discussion on energy conservation, or maybe we'll finish our derivation, and maybe I will finally present what are the equations that you will solve for to in the convection type problems, and then we will solve some numerical problems next week, week 8. Okay. All right. If you have any questions, please feel free to stay back and ask. And if you're not, then we will meet next week, the same time, 7 to 9. Okay. Thanks for attending. Thanks, Avinash, and thanks, Krishna Kumar, and also the other two people who attended, and also the people who are going to view in the YouTube. All right. Thanks for attending. Bye bye.